Okay, so the constant quantities in this situation are the length of the original sheet of paper and the width of the original sheet of paper are both constant quantities. Okay, so changing quantities. Yes, sir?
The size of the cutout.
Size of the cutout. Okay, so let's I'm make it a little bit bigger here so we got more room. Okay, there we go. And so I can, they're squares, so they just have the side lengths from there to there. So the dimension, the side length dimension of the square cutout. And I think they say it was X on the worksheet. Well, we're saying it's X. So we're going to define the variable X as the cutout side length in inches. So that variable X can take on all the values that the cutout can take on. So we want to determine what are all the values. Is that a question? Although we're going to focus, I'll get to you in a second. So let's talk about, so remember the variable is a letter that can take on all the values of the quantity. So we want to define what are all the values of the quantity that in this situation that X can take on. So what are all possible values of X? Or what are all possible values of this quantity's cutout side length that X can take on? Okay, he wants 0 to half the width of the paper. So let's start with the minimum. So what about 0? Can X take on a value of 0? Okay? You would, what's that? You would never, so can I take the sheet of paper and can I cut out squares of size 0? Okay, I'm going to do it actually. Ready? I just did it. There it is. You see? So can X take on the value of 0? I know. Why is it uncomfortable? Because you don't what? If you say X equals 0, what happens? You don't get a box. You don't get a box. But as we've defined X as a cutout side length, can it take on the value of 0? Does it have meaning? Does it have an okay meaning? Yeah, you just don't do anything. You just hold your sheet of paper. It's okay. It's okay that you don't get a box, okay? Because it's we've defined X as the cutout side length of the square. We can make it 0, and then we just have a flat sheet of paper. What about X equals negative 0.5? Can I cut out squares of like negative 0.5? No, right? So negatives, for sure, don't make sense. But even though we don't get a box, X equals 0 mathematically is a perfectly legitimate value of X. It means no cutout squares, okay? So that's our minimum. What's the largest value of X that's possible? It's the largest value of X that's possible. Okay, I'm hearing 4.25. What do we think? So first of all, X can be as low as 0. The minimum that X could be is 0. That's okay. Of course, small values, 0.1, 0.5, 1 inch, those are all fine. So where do we run into trouble? What's the highest value of X that is possible? 4.25. So, same question. Does it have to be strictly less, or can we cut out squares of 4.25 inches? Can X be 4.25? All right? What do you get? You just get a flap of paper that you fold, and you don't get a box. You just get this flap of paper sticking up in the breeze, okay? So, but is X equals 4.25 legitimate value of X? What about greater than 4.25? Now think about, so can I get, out of this bottom side of the paper, can I get 2 squares of side length 5? Can I do it? No, once I cut my first one, it's impossible. Once I start cutting my first one, that's 5. There's no way I can get this second one of 5. But I can get 2 squares of 4.25 off the bottom of the paper and off the top. So again, you don't get a box, but as a possible value of X, it's perfectly fine. Okay, that's called inequality notation, interval notation, looks like this. You use square brackets for including the endpoints, and you use parentheses if you not want to include the endpoints. We want to include the endpoints because we can cut a square of length 0, it's okay, we can do it, and we can cut squares of length 4.25, it's okay. Now, the interesting cases are all the ones in between, right? So all the ones in between give us a valid box, and that's what's more interesting. But this is looking at all possible values of x. Okay, so, sir, you had another changing quantity back there. What's your name? Naz. The height of the box. Is it changing? The height of the box. So as I change the cutout length, does the height change? Can we define that height in terms of the cutout length? What is it? Some people are saying x. Isn't it 2x because there's an x here and an x here? X or 2x? It's just x because when you fold up, those x end up at the same place, right? It's the height of the box is that dimension of your flap, right? And you fold your flap up, and the height is x. Okay, another changing quantity. The perimeter of the base. So as I change x, does that perimeter of that base change? Yeah, it gets less, right? It gets less. And so what is the perimeter made of? What comprises the perimeter? Yeah, what quantities comprise the perimeter? What quantities? The length and width. All right, so let's call the length. We call the constant quantity of the original sheet of paper, its length, capital W. We'll call the length of the box cursive L, and then the width. So notice, do those dimensions change when I change the cutout length? Yeah. As the cutout length increases, what happens to the length and the width? They decrease, right? They decrease. Okay, another changing quantity relative to the box. Jackson. Volume of the box. The volume is, for a box, is length times width times height. Okay? So let's go back. So in order to get the volume strictly as a formula in terms of x, if we could get all three of these in terms of x, we would have the volume in terms of x. So we've got the height. The height is x. Right? The height of the resulting box is however big we cut off the square. So let's look at L. So where in this picture is this L, this changing resulting length of the box being shown in the flat picture? Can anyone describe where it is? Yeah, Shruti. Aside from here to here?
No, the small one.
This one?
No, the woody one.
The what?
Woody one.
The vertical one? Starting where?
Starting from the other side, the small woody one.
The dotted line? Oh, this line here.
Yeah, right.
Okay, so she says from here to here is the length of the box. Agree with that? Which would be also this dotted line right there, right? That's right. That's the length of the box. Okay, so how can we write that length in terms of x? How can we write that length in terms of x?
Big L minus X.
So did you say big L? Is that what you said? Yeah. Remember our big L was the constant quantity of the original length of the piece of paper. He wants big L minus x. What do you think? You want to change? He wants to change now. You lose an x here, right? So you got this dimension is the original sheet length. You lose an x there, and you also lose an x there. So we want that length less how much? 2x. But we know what that L is, right? What's the L? That's that constant quantity. We don't need a variable for it. I called it L, but we know it's 11 because it's constant. All right, so we got L is 11 minus 2x. What about the width? So where does the width show up in the flattened box? Where does the width show up? Somebody knew? Yeah, Moises. He said the horizontal dotted line in the green area. Is that the width? Yeah, from here, and that's the same as from here to here. And that's our changing width of the resulting box. How can we write that in terms of? So our constant width of the original piece of paper is 8.5. And it's going to be shorter by how much? By an x over here and an x over here. So minus 2x. Now we're ready. Now we can write the volume in terms of x, solely in terms of x. What was our length? 11 minus 2x is our length, given a square cutout length. Our width is 8.5 minus 2x, and our height. So we've got a formula that gives us the volume of the resulting box in terms of whatever x we cut out of the square. So that x, right, can take on all values between 0 and 4.25. Say it takes on 2.5. Cut out squares 2.5, plug 2.5 into the volume equation. It'll give you the volume of the resulting box. Okay, so we're going to focus on these two right here. The length in terms of the square cutout and the volume in terms of the square cutout. Let's kind of analyze those and break this down here. Any questions on the setup here? Any questions on what we've done so far? Make sense? Okay, so we're going to start with the length, okay? So here I'm showing the cutout length, cutout side length in inches on our horizontal axis. And I'm showing on the vertical axis the length of the resulting box after we cut and fold. Okay, and so the cutout length is represented by this blue arrow. Whatever the current value of x is where the blue arrow is. The corresponding current value of the length is the purple arrow. And then that's shown in the illustration up there. So when x is 0, was x equals 0 a valid cutout length? Yes. Okay, ignore the blue squares. There it is. What is L in that case? What is the length of the quote-unquote box, even though it's a flat piece of paper? 11, and that's showing that point right there is 0, 11. Okay, so as we've been doing lots of, we're going to make a table of delta x and delta L. And we're going to build some ordered pairs of delta x and delta L. Okay, so this first ordered pair, 0, 1, or points on this graph, do they correspond to ordered pairs in this table? Points on this graph, are they the same corresponding to our ordered pairs in the table delta x, delta L? What do you think? Yes or no? I heard some yeses and some nos. Question is, we're going to get a graph here, right? And the graph consists of what? What does the graph consist of? Points. These points are ordered pairs. Are they the same as these ordered pairs in this table? No. No, because the table is the changes, right? Changes, not the quantities themselves. We're graphing the quantities themselves. We're graphing x and L. Our table is going to be of the change. We're going to analyze changes. So the first change I want to do is I'm going to cut a really small, or I'm going to increase the cutout length from 0 to 0.5. What's the value of delta x? If I go from 0 to 0.5, what's the value of delta x? 0.5. And the question is then, what will delta L be? How much will the length change if I increase the side cutout by 0.5? What's that? How'd you get that?
0.5, and then it's subtracted from
So were you thinking about this, thinking about removing 0.5 on this side, removing 0.5 on this side, and what will the resulting purple length be, right? So the change will be, she said -1, agree? Yeah, it's a decrease, right? That length decreases by 1 inch because we cut out ½ an inch on either side. So let's do it, watch, here we go. So I'm gonna, right there, okay? So I just increased x by 0.5, and let's show that here. Why not? Help me. I increased x by 0.5. How much did L go down? 1. So there's my delta x of 0.5. There's my delta L of -1. Okay, I'm going to do it again. I'm going to increase x from 0.5 to 1. What's delta x? Still 0.5, right? So now, what does this represent? It represents I'm going to increase the cutout length from 0.5 to 0.5, from side length of 0.5 to side length of 1, which means I'm increasing the cutout length by 0.5. What will happen to that length, the purple bar? What will the change in length be? -1 again? Let's see. I'm going to increase from 0.5 to 1. That's increasing the cutout length of 1, or of a half. Does it go down 1? Maybe. Let's see if I can get it. It's touchy. There we go. So I did the same increase of 0.5, and you're telling me it should go down 1 again. Did it? Okay, what about an increase from here? So now I'm going to start from here. I'm going to go from 1 to 2. What's the increase in x? What's delta x? 1. How much will delta L, what's the change in L? What's the change in length? You're all saying -2. Why? So who can reason? Why negative? Why will the length of the remaining box decrease by 2? Gee.
Because the difference from 0 to 25 is -1 and it's constant with that. So if you double that, you get -2.
Okay, so what you're seeing is that you have some constant multiple here, is that right? That changes in L are always what? Can you finish the statement? 1/2 delta x. What do you think? Delta L is 1/2 delta x. That's what someone said. 2 times delta x. -2 times delta x. Given a change in x, how much will the length change? Well, you got a corner on each side, right? You take off a corner on each side. So you're going to take off 2 times however much you increase x by, and that's how much the length's going to decrease by. So there it is. Okay? So if I go from, now I'm doing a change of 1, from 1 to 2. Let's do it first. So here's a change of 1 from 1 to 2. Resulting change in L. Now, equals -2. Okay, let's do one more. So from 2 to 3.5. You finish it. What's delta x? What's delta L? What will the picture look like? Go. So what's delta x? What's delta L? And imagine what the picture will look like. Where's Nicole? Talk to me. Was I calling you last time? No? Okay, cool. Nicole, talk to me about this. I'm going to change x from 2 to 3.5. 1.5. Right? To get? So if I took if I increased the side length by 1.5 here and 1.5 here, how much would L go down? -3. It would go down 3, or a change of -3. Does that maintain the -2? Yep, so let's watch it. Ready? Here we go. So we're going to increase side length by 1.5, and L goes down 3, or changes by -3. Okay, so from the beginning, these are all possible points of side length and resulting length of the box. Cutout side length, resulting length of the box. What characterizes all the points? If we wanted to graph all the points, what will it look like? Right, we said, so what kind of rate of change do we have? Constant rate of change graphs as? Straight line, right? A straight line. You always have your changes. Change in L is always -2 times the change in X. Any questions on that? So that's a kind of a review of what we did the last week or so. So let's look at value now. So now, same cutout side length on the horizontal axis. That's the blue arrow. It's the current value of X. The purple arrow is the current value of the volume. Okay? So again, start at, we said cutout length of 0 is fine. Volume of our box. Volume of our box. What is it? 0, right? No volume to that. And that's shown by that first point right there. What did we say the volume equation was? Let's write it up here. Volume equals length times width times height. Length times width times height, all in terms of X, okay? So this is what we're doing. So we're going to do the same thing. We're going to look at changes in X and resulting changes in volume. So these points in this table, are they the points on the graph? The points in this table, the ordered pairs, are they the points of this graph? No. Those are the changes, right? It's a different quantity than X and V themselves. So I'm going to start with a change, again, 0 to 0.5. What's delta X? 0.5. What's the corresponding change in volume? This is part of what we did Friday and you did for your homework. Go, find the change in volume for this initial change of 0.5 in the cutout length, 0 to 0.5. Go, find the volume. Change in volume. Find the change in volume. Where's Ryan Disworth? So take me through the process. Even if you haven't got the answer yet, take me through the process. So you plug in the 0.5 into for X. Okay. 42.5. So in general, can we take the change in X, plug it into this formula, and get the change in V in general? Okay. So instead, what do we need to do? Where's Jackie? Jackie's on. You here? Where is James? Jimmy. Where's Jimmy? All right. Tell me. Okay, this X? So we're going to plug 0 into that, and you get volume equals 0. You plug 0.5 in, and you get 37.5, and then what? So we need the difference of those. So 37.5 is the change. The change is We did lots of practice a couple weeks ago, or a week and a half ago. How do you calculate a change? Final value minus the initial value. Okay, so erase that so it's not confusing. Okay, so let's see that in action here. Oh. So I'm going to increase the side cutout length by 0.5, and we should see that point jump up to a volume of 37.5 when I do that, if we did the numbers right. Did it work? It did. So this 37.5, is it the volume of the box right there? Is that what that is? Is that what that represents, that 37.5? The change. How do we represent the change? Yeah, so here's our change in x, delta x. That's our 0.5. So that change in volume is represented not by the pink arrow, but by this line. That's what that 37.5 that we calculated was. Make sense? What's the pink arrow represent? Pink arrow, what does that represent? Current volume, right? The volume of a box. This delta V is how much it changed from what it was before. Okay? Lost it on the 5 there. Let's try that again. Okay, do it again. So, from 0.5 to 1, what's the change in x? 0.5. So the change in V should be 37.5, right? Well, equal changes in x mean consistent changes in V, right? Find the change in volume. Go. Find the change in volume. Where's Anthony B? Where's Anthony? Talk to me about the process here, Anthony. Plug in the first x. Okay. 37.5, then. Right, we got to get the volume, the starting volume, and the final volume. Right? And then what'd you do? Okay, and what'd you get? Exactly? Did you get 21? Okay, how can we show it on the graph? So we want to show the change of x and the change of y. How can we show it? Change of x. Horizontal change like that. That's our change of x of 0.5. And let's watch if we did the numbers right, let's watch the arrow. So if I go over if I increase x by 0.5, I should get an increase. Well, no, look, it's like almost 60. I thought you said it was 21. Okay, 21 is the change. This is what does that represent? That almost 60. Current volume of the box. So delta V is 21. Okay, so what's going on here? I thought that equal changes in x result in consistent changes of y. We've been saying that over and over again. I don't know what that is. Talk to me in terms of changing quantities. Talk to me in terms of changing quantities. Why? Is it right? Are our numbers right? Yeah, and the graph is showing it's right too? What's happening here? Not right. Change is not constant. So the changes are changing. Over here, changes were constant, right? Every time you went 0.5 in x, you went down 1 in L in length. Every time you went 1, you went down 2 in length. Every time you increase that cutout length by 1.5, you go down 3. But now, changes are not constant. So do one more. Do 2 to 2.5. 2 So 2.5. Find the change in volume. What's the change in x? 0.5, right? Is Grant here? Grant. Where's Grant? Did you get either volume? Did you get a volume yet? Just a volume. Okay. Two, starting with 2 and ending at 2.5. That's an arrow. It's an attempt at an arrow. So talk to me, what would you do? What's the process? So which number do you want to plug in for x? 2. Did anyone get the volume at 2? What is it? I'll show it here. So at 2, you're saying it's 63? Maybe? 2 is 63. There it is. There's the pink arrow at 63. All right? And so then what do we do? Plug in 2.5, and what do you get? 52.5? And to get the change in volume, take the final value minus the initial, makes sense, and you get negative, what was it? 10.5. Okay, so here's our starting point. I'm going to increase this cutout length by 0.5. And did the volume go down? Yep, and I should have tracked that first point. I think somewhere up here. Okay, so there's our delta x. Corresponding delta v now is negative. What's happening as we're cutting bigger squares? Now the volume for these tall, skinnier boxes is going down as you cut bigger squares. All right, so let's look at the whole thing. So someone said a parabola. That's right, it's a parabola. But all we need to know for now is that it's not what? And the graph, therefore, don't pack up. We got a whole other thing to do. So please don't pack up. I'll go as fast as I can. Here we go, ready? So now as our square cutout length increases, the volume changes, but not constantly. We start getting larger and larger boxes, and then we get to a point where we keep cutting larger squares. Now the volume's going down until we get that last box where it's just, so like a box like this has much less volume, the big squares, than this box, right, with the smaller squares. So initially, volume goes up, but then as you keep cutting larger and larger squares, volume comes down. All right, so what is the formula for delta V? So delta V equals K delta X. What's our K? What's our K for delta V equals K delta X? What is it? What are your ideas? What should we, how do we? What's that? It wasn't constant rate of change. He's saying it's not constant rate of change. So what are you saying? There is no K. Is this right? Is this right? No. Remember? Constant rate of change. Our constant rate of change for side length was -2. But we don't have a constant rate of change. So we can't just simply crank out changes in volume given changes in x this way. We have to go through this process of getting the final volume, initial volume, and subtracting every single time because the rate of change is not constant. So you can't, this is no good. Okay? You can't, there is no delta v equals k delta x because it's not constant rate of change. Okay, quickly. Any questions on that? So here's the transition now. So we're talking about any kind of rate of change now. So this is changing. Talk about constant rate of change. Now this is changing rate of change. Questions on the volume or the change in volume? Okay, so there's notation here. No, not that one. Shoot, it's this one. So this is the idea of functions, okay? A function, it's aptly named. It has a function. It does something, okay? It has a purpose or a function. And we have a function here that takes the length of the side cutout and cranks on it with this formula and spits out what? Volume. So this formula does something, right? It gives us a volume if we give it the size of the square. So in general, we call that initial thing that we give it the input. And the function does something. It takes that input and gives you an output according to some rule. There's some rule that it acts on the input to give you output. Okay? So just remember, why is it called a function? Because it has a function. It does something. Okay? So quickly here. So here's the notation. The volume was the output. Okay? F is the name. It doesn't have to be F. It could be G. It could be H. It could be P. All right? F is the name. You need this for your homework. All right? The input, we called X is the length of the side of the cutout. That shows up in this, next to the name, in the parentheses, and also shows up in the rule. And that's the rule, okay? So quickly, of all these things that I've said, this whole notation right there, what is that? Of all the things that we've named here, what is in the blue box? Is it output, name, input, or rule? It's output. When you see that notation, that's output. So for instance, what is f of 2? When you see that whole thing, what does it represent? But what is this whole thing? Does this represent a square cutout of 2 inches? Is that what that represents? No. Does it represent a volume equal to 2? No, it equals a volume. What volume does it equal? When the cutout is 2. When the cutout has a side length of 2. So we're going to practice a lot. When you see that notation right there, you got to get in the habit of thinking, that's the output of the function when the input is 2. That's the output of the function when the input is 2. Okay, I'll try to get Wednesday's web work up shortly. I wrote them this summer. Normally I don't, but I was given the task of writing them this summer. Yeah. Why do you ask? Okay. Do you think it's helpful or not?